All right, second attempt. Tried to stream this the other day, did not go well. Turns out no audio was recorded at all. So hopefully it'll go better this time. Although now that I said that, I need to mute to sneeze. Oh yeah, quality productions here. Quality caster and everything. So this is part three, and I promise it's the last part of sort of an exploration we're doing into what was originally the front end challenge from Dev.to. I say originally because we got distracted a little bit by solar planets. In part two, we implemented a planetary ephemeride calculation in a self-contained library that we're going to use, and that will update specific positions of the planets and let us trace the orbits in real time. In part one, what we had put together were basically circles, and that's not realistic. They were all within the same plane. All the planets were lined up. We'd rather see a realistic depiction of the solar system and where things are. So that calculation will pull in that module, and it'll help us do those position updates and point calculations for the line. And then we're going to finish sort of the requirements for what was the challenge. I think we're like 2.5 weeks late now or something like that. Specifically, where we had left off was looking at raycasting to do collision detection and using that to trigger what we're going to do are some mouse over effects for specific planets, and then actually presenting the dialogue of the information from the markup that was sort of the core to the original challenge. The main motivation behind this is I went back and looked at sort of the Dev.to challenge inspirations, the projects inspired this, and as it turns out, there was one already that was doing like 3JS material shading and some really cool stuff. I would love to go into shaders at some point. That's not sort of the purpose of this, and for the purpose of doing something unique and a little bit different, and making sure this isn't just copying something we've seen. We're going to focus more on the planetary states and show how those things take place. So without any further ado, let's lead it up. Here we go, where we left off last time. So the first thing here, before we get started, is we're going to add our solar planets dependency. This is, actually, I'm not sure if I had ever shown this, so let's go ahead and pull it up. npm js. Oh, it's not, or it's com. I can never remember that. In part two, we had put together the module I mentioned based off an algorithm from the Curtis text. And we since did a basic yarn publish with the appropriate credentials, and voila, here we are. Pretty cool, right? So we can do a yarn add here, and that dependency is now included in the project. You can see our package has been updated, and now if we run, we're going to do this in dev mode for hot module placement. There we go, 5173. And we're back. All right, so this is where we left off, right? We had 4 inner planets. Actually, let me make sure I don't forget that. Add outer planets. And they were all in flat circles, and they were all lined up. So let's start off there. Let's use our the API for that package that we had developed to compute the actual positions of the planets. Sound good? Sounds good. So let's go in here. We're doing everything in a single module for now. It's going to get a little bit messy as we add more and more, but honestly, for the scope of this, it's fine. We could talk about how this might be better organized ways to break it out. That's probably best left for a bigger project. So let's start with, we have basic planet information here, but this is not all the information we need. So if you recall from part 2, we had a specific catalog built into that package we use for testing. We're going to go ahead and just grab that here since it's a static asset. We call it the Standish catalog where it was originally published. Voila. So here's all the details, right, specific to that model of planetary ephemerides. We get the orbit elements on their drift relative to some reference, in the case of J2000. So let's pull up that interface and remind ourselves exactly how that worked. We'll go ahead and import solar planets. Voila. And then in our factory here, let's say import, we'll do this as raw. Should we do it as raw? Yeah, let's do this as raw. Then we'll parse that. Okay, there we go. We have the JSON. I think, let's see, we're going to want, I'm trying to think if we want to parse this all at once or, yeah, let's do that. Let's do something like this. So we'll have a dictionary of those entries, and then on window load, we'll just say parse catalog details, app catalog. No, right, I called it that. Okay. All right, so far so good. And now when we instantiate, we'll need a name. So let's add that here. I think we just called it name, right? Yep. We have a new parameter here. And from that name, let's remind ourselves of what that lookup. So it's a lowercase catalog entry. What do we call that? So I think we called it planetary elements. Planetary orbital elements. All right, so const, we'll call it that. If it has it, window app catalog name to. Otherwise, no. Okay, so now we construct the mesh. We're going to want to set the position. Everything else is still the same. And we'll include that just as a fallback. Okay, so here's the fun part, right? Solar planets, get RV from, let's see, const RV. We're not going to use velocity, so elements, date time. Okay, so planetary elements and date time. I think what we're going to do here, there is a clock model in 3JS. Off the top of my head, I can't remember exactly how that folds into the scene, but we're going to do this. That way we can change this as a part of the state of the application just to like demonstrate, hey, we're going to fly around, right? So DT in this case is going to be window app now. Okay, let's say Yep. We'll get that back in kilometers and then mesh position set. So we have some sort of scaling just to keep things visible. That is an array, so we will go X, Y, Z. All right, and that should be enough to set our positions with our handy dandy library here. Let's see if that worked. Hey, check it out. These are the current positions of the planets. So a couple of things you'll notice. First off, these are really small. I think we might expand. We had some sort of scale set right here. 10 times seems a lot. That should probably be a parameter too while we're at it. Let's see, radial scale. So spatial scale was for displacement. That looked a little bit high. Let's go 200, just to keep our eyeballs happy here. All right, here we go. That's a little bit better. One thing you'll notice, of course, is that our planets have actual positions. The orbit traces do not. These are still circles. So how are we going to do this? We still need to compute the points. We need to compute the points for one period of rotation, right? That the main input for our interface is a function of time. So what we'll do is we'll start from the current time, we'll sample forward in one period for some number of points, which we're already doing, but we'll use a different call for that time to make sure we're doing the right calculation. So in our orbit trace function here, we're still going to need the name because we're going to need to look up the elements for the call. Orbit trace p name, there we go. Okay, so we still have a set of points that's still going to result in some geometry that we're going to create a line from. It's just this that changes, right? So let's do the same thing here. Fall back and here we go. All right. So from window app now, and then one period will be a function of the orbital elements, of course. We do have some helper functions for that, I believe. Oh, no, we don't. Let's add a helper function for that. Get period from POE. Technically, this changes a little bit as the sim major axis is a function of, or the orbital period is a function of sim major axis, and that drifts a little bit with respect to our model. Since we're just coming up with points to sample over time, that's okay with us. We'll just use the fixed sim major axis value here, which we will need to convert from AOE. So POE dot, was it SMAAU, I think? AAU from our models. And then this is actually an equation we've talked about before. That's fairly useful and fairly straightforward. I think we were talking about this actually when we were going over units as a unit example, like dimensional analysis. So given some major axis and some gravitational parameter, you can compute the period, and this ends up being in seconds. That's true for Keplerian elements in general, by the way. So we had talked about it in context of satellites, but it works for planets here as well because they're using the same orbital model. So 2 times, say, in seconds, 2 times math pi times math square root math pow. Divided by, I think we used the global gravitational parameter. Oh, did we not export that? We might not have exported that. We did not. Okay. Cheat just a little bit. My favorite package manager, control copy, control paste. Where'd we go? Where'd we go? All right. Yep, here we go. Okay. Divided by mu. Now we'll give it in seconds. Oh, almost forgot. Let's convert that to kilometers. Okay. All right. So let's t in seconds get period. And now we can sample, right? that will. All right, so the date time is going to be, let's see now, T0 value, let's see, new date, T0 value of in milliseconds, plus T, let's see, in milliseconds, zero, so that's the total period, and we need some fraction of that period, specifically I over n. That will all go from 0 to 1 inclusive because we did n plus 1. Okay, that should work. Now we have enough to say our unused velocity, solar planets. Here we go. Get RV from, say, POE. Daytime here is T. And now we can add those points. So let's vector 3. And we actually have a third dimension now, but we need to treat everything consistently. So R0, call this in the heliocentric equinoctial frame. 1 or 2Z. Okay, that should be enough. Let's check it out. Ready? Nope, didn't work. Why didn't it work? Oh, that's a lot of luck. See, 128. Let's disable that. What else are you failing at? Bounding sphere. Position. We're not setting position correctly. Push new vector 3. Spatial scale. That looks like it should be a vector unless. No, that's working. Right. Must be this. Call stack's probably going to point there, isn't it? No, that's specifically for intersection. Boop. Boop. So why aren't you getting the lines correct? 0 now. Yep, that helps. It's always nice to return a value from your functions. That's a good thing. So a couple of things you notice now. First off, the planets are actually on the traces. Great. Also, they're three-dimensional, right? And they're a little bit elliptic. How cool is that? Okay, not bad. Not bad at all. So with that, we've actually taken care of what? Orbit positions, orbit traces. We're happy. So let's go back to the raycaster now and add those effects. So we had demonstrated sort of how the 3JS raycaster works here. And now we will want to actually handle those collisions. So there's a couple of things we want to take into consideration here, but for starters, let's just sort of debug or demonstrate the fact that these collisions are taking place. First off, I actually made a mistake last time when we did these calculations, and it took me forever to figure out. So I'm going to go ahead and fix this now before I forget. The y coordinates flipped for the camera's projection matrix and the scene coordinates. So I have to not be a dumbass. That always helps, right? The next thing is when we handle these collisions, there's a couple of things that we need to take into consideration because we have some behaviors we want to support. So first, let's iterate through this intersections array, and we're going to say that there's some sort of handler, and it's going to process how many actual collisions, because this will get all the collisions through the scene, right? This is recursive by default. It's going through everything in the scene. Not everything in the scene, like the orbit traces, will be an actual planet, or it could be the sun, it could be the axes, or anything else. So uh, we're going to say we'll have a number of triggered behaviors. That could be 0, it could be 1, it could be more. And then based off of if there were no triggers, we'll want to reset certain states that we're going to change as a result of mousing over and doing other things. So that is we're going to have a process collision function here that says, okay, there was an intersection of some kind. We don't know if it was a collision, and it's going to return a value true if there was and false if there wasn't. So what this is basically just going to let us check and make sure were we over a planet, were we not over a planet, and now that return value, and then the handler here that returns that value is where the magic is going to happen. So let's, in that collision model that we saw, one of the parameters, one of the properties of an intersection was the object. So we'll get the name of that object. I think we had, let's see, let's make sure we're actually assigning that. We might not have been assigning that in our factory. Let's make sure we're assigning that. Mesh, mesh. Yeah, we're not assigning that. So, okay, if it's not equal null, mesh name equals name. Okay. All right. And since that's going to be used for a query, we're going to need it to be consistent because we reference it different ways across the catalog. Okay. Here we go. Here we go. Here we go. All right. So now we get the object name, which we know actually exists. That always helps. And we're going to say we know there's a certain number of names in our what do we call it? Our initial sort of interface information of the planets. And we're just going to make sure we can correlate them here. If it's something else, the name will be empty. So let's make sure that it's included. If this is true for now, we're just going to debug it, make sure this is working correctly. And then we want to return true or false, depending on whether or not that met our expectations. Okay, so let's mouse this guy over and try out some planets here. There's the sun. Here's the Earth. Bonk. Nope. Bonk. No, that's not working. Why is this not working? Oh, we need to set a scale for collision. So let's good factor. Honestly, there's probably a better reason for this. Mesh factory. Okay. Let's set to. This is going to double the size of the mesh for collision. So some of these are kind of small, so that didn't work either. Oh no. Oh no. Huh. Okay. It might be like that, why don't you? See, radius, mesh, yep. Raycaster, winter move. Yep. Set camera, mouse position, camera, intersections like 0 for each process collision intersection. Let's map name. Names includes name. Okay. Try to do responsible debugging here. Hey, so it is being triggered. Did we not set the name correctly? Oh, right, because we had normalized it. Ah, silly me. Silly me. Okay, so we're gonna query there, and now we should see. Bonk there. Okay, cool, much better. All right, so we want to trigger some sort of behavior. What do we want to do? Well, let's look at our plan here, right? First, let's do some basic mouse over effects. So let's say we want to indicate this is clickable, so we'll change the cursor. And we want to indicate you're clicking on that planet, so we want to, change the color to indicate, hey, this you can click on this thing. But we also need to make sure those are resettable once the mouse leaves that area. So that's one of the reasons we're counting collisions here, because we need to revert to sort of the default state. And that's not easy to do with raycasting. You have to keep track of those things fairly carefully, unlike like mouse in, mouse out, right? So let's consider a couple of things here, and then finally we'll handle clicking. But for now, let's just do the mouse over effects. We want to change planet color, and we want to change the mouse button or cursor. So the planet color, we already have a reference to the intersection object. We can get the material, and in this case it's just a standard basic mesh material, so we'll say set that color. And then we'll do a little bit of cheating here for the cursor, since that's stateless from the browser. Pointer. Okay, and now down here, when we reset the state, we'll say style cursor inherit, and then iterate over all the planets to make sure the colors match the interface model that we have here. Let's see, how do we want to do this? More to the point, how do I not want to mess this up? Okay, planets from we'll get the scene graph node from a query against the scene object by name. This is why we had normalized it, so we could query that name property. Okay, so yep, okay, and then make sure that we actually get a scene graph node before setting the color back to from the planet model here. What do we call it? Approximate color hex. There we go. And 3 does let you set color values from a wide variety of things, including if you assign this in hex, it's like an integer equivalent value that it will interpret accordingly. So that, let's see if that's enough. I think that should be enough. After a little bit of HMR love. Oh, our sun's really small. Our sun shouldn't be that small. Okay, bonk, bonk. Hey, look at that. I like it. I like it. I like it. Cool. So it only works with planets as intended. Okay, so now if you'll recall, the actual markup we had, we're supposed to process here, or extend for the challenge, is here, right? So let's, how do we want to do this? You know what? Yeah. Let's just copy this in. We'll hide it all at first and then query it later. Trying to be as faithful to the original requirements as possible. So basically, the only difference between their markup and our markup now is the fact that we're including the style sheet and sort of the source module, right? And then Feet goes off and does the rest. Of course, now we need to actually take all that stuff and hide it, because it's going to do fun things to our flow here. So we will say all headers and sections and articles are hidden. Header section. Hey, look at that. Oh, and there's a copyright. Copyright? Who copyrighted it? This is for a challenge. Okay, and a footer. So now, we can go ahead and do class query, let's say for planet Neptune, right? So window document body query article planet Neptune. Voila, to get the article content. So why is that important? Because we're going to use this when there's a click event. Did we do? So we have this mouse position. We're also going to add an is mouse down. Eventually, in a real application, you'd want to have some sort of encapsulated model for mouse control. But in this case, just the position and the down states are fine. So let's add those. Window add event listener. Mouse is down. Is it mouse button down? Yeah, we'll do mouse down on mouse down. Mouse up. And really the sole purpose of these functions, of these handlers, is going to be to change that state. So now if we go to our collision handler here, what we can do is if it's over now and the mouse is down, we're going to open our dialog. What, pray tell, is our dialog? All right. We'll use a very rudimentary dialog approach here, in which basically it just pops up HTML. It'll be absolutely positioned. It'll be modestly styled. We just want to show the information about the planet, right? And then we'll populate it with the markup from that portion of the article, queried with the query selector. And then, of course, we'll want to close it. We'll close it when, let's say, the mouse goes. Should we do it on out? Yeah, let's go ahead and do it on out so we can just keep this consistent here. So, we don't have really a UI library here. For purposes of keeping the markup consistent, we'll avoid changing the body and ingest this dynamic or inject this dynamically. So let's say it's not going to be a true dialogue. We're not going to overlay everything. And we're going to manually hand jam it here. All right. Then let's query article content and to populate dialog. What do we say? We used what? Article dot planet dot. Okay. So we need the name of the planet here. We are mousing over. We can get that from here. That should be lowercase. Yep. So window document body query selector. Article planet name. Dialog, inner HTML, article. Be careful with this. Assigning inner HTML, especially if you're doing it in large quantities, is actually a really expensive operation. There's all sorts of like string parsing and deserialization the browser goes through. Even though it's a baked-in method, like part of the DOM API, it can bite you in the ass if you're not careful. And then here, to close it, we'll just say, get that dialog. We don't care if it doesn't exist. But if it does, style display. All right, now we're ready to style it. Oh gosh. Um, just sort of. Um, Obviously, just sort of randomly guessing at what this might look like. Let's try it. Ready? Click. Nope. Class name add. Did I get that right? Dialog. Query selector. Yep. Create element. Document create element. Doesn't exist. Oh, list. Da. Okay, how are we doing on time, by the way? Prefer to keep these shorter, closer to 30 minutes. We're at 37 now. Fortunately, we're almost done. We won't do too many shiny things after this, but no, it's not airing. That's right. We need to actually make it visible when we click on it. Okay, we populate it. What else is going on here? Canvas dialog, style display. Positioned. Oh, yeah, okay. Yeah, but I'm position absolute. Yeah, like that. Looks like we need some text color. Yay. Not bad. Not bad. Let's see. How does everything else show up? There's Mars. There's Mercury. There's Venus. Hey, that's pretty cool. I don't mind at all. A couple of things here. When we created the sun here, I'm going to scale that by the same factor so it doesn't look so teeny. Let's see, what did we call that? Scale factor? Radius scale? Radial scale. This actually might end up being hideous. Yeah. Don't need to use the same radial scale for the sun. This is different from the displacement scale. Let's just say 10. Okay, yeah, that's much better. All right, So the last thing here, let's see, what have we done? We triggered mouse over effects. We had the on click dialog. We've really finished the challenge here, but for the most part, except for we want to add some more planets here. So spoiler alert, I've typed this up and we'll just copy it in so you don't watch me paste information from Wikipedia. Let's see, Jupiter, Saturn, and we just chose some modestly interesting colors for this. Honestly, I just like eyeballed these, but let's see. We have a full catalog with them, so we should see them show up. Voila! Check it out. Check it out. So, fun fact: if you look at the Earth, right? Actually, let's make sure this all lines up. Okay. Yep. Bonk. Saturn. Jupiter. Cool. How cool is that? This is so awesome. I love it. I love it. Okay. So if you think about the Earth here, right? Like now we're getting to really like Kerbal level stuff. This is pretty cool. So if you're a midnight, what that means is you're on the opposite side of the Earth from the sun, right? So now you can actually start doing some basic estimation of like, okay, given where you are in the Earth, there's the zodiacal line or the ecliptic through which most, this rough plane through which most of the planets pass. And you can start doing some V&V. Just like go out tonight, take a look. If you're, close to when this video was recorded, at least, you shouldn't be able to see Venus, and except, let's see, rotating this way, right? Earth's rotating this way. So you might be able to see it in the evening, right? Right after you go behind the sun, you might be able to see a brightly lit Venus. But then at midnight, you shouldn't be able to see Venus. It should have set. You'll see on the eastern horizon the rising of Mars, right? And Jupiter should be in roughly the same direction. It'll be not quite as close to the horizon, right? And then Saturn should be roughly almost right above you, at least on the zodiacal plane, of course. So cool V&V. You could actually, if you had a telescope, you could see Uranus, but you will not be able to see. Actually, what am I saying? It's right here. Be able to see Neptune too, roughly the same direction as Saturn. So yeah, go outside tonight. Take a look. Help me with some V&V for our little solar planets library here. Okay, so that does wrap up the sort of excursion here. Random software projects is what I'm starting to call these because, well, they're random and they're software projects. I promise we'll get back to engineering. Next up is dynamics. Oh, that should be a lot of fun. I hope you'll join me, and I hope if you didn't learn something, I hope you were at least modestly entertained, vice versa. Take care.